welcome everyone to the Algebraic Graph Theory Seminar. This week we have Karami, who's going to be telling us about perfect color to the Generalized Petersen graph. So I'll let him take it away.
Okay, can I start? Okay, thanks for the introduction, and thanks to the organizers for giving me the opportunity to talk about perfect colorings of the generalized Petersen graphs, and thanks for the audience for coming in. Today we are going to talk about perfect colorings of the generalized Petersen graphs. This material is based on the following works. The first one is a joint work with Mehdi Alayan about perfect two colorings of generalized Petersen graph, actually GP NN2. The second one is a joint work with Mehdi and Sajjad Siyasat about perfect three colorings of GP 5 and 2, GP 6 and 2, and GP 7 and 2. And the last one is about perfect two colorings. I call the first one by AK16, the second one by AKS18, and the third one by K20. Here is a rough outline of what we are going to talk about. At first, we give some introduction and historical background about perfect colorings. And then we go on talking about perfect two colorings and perfect three colorings of GP, N, and K. Let's start with the definition of completely regular code. In a regular graph G equals C, in general, we define a code, a subset of B of G. A code C is called completely regular if for all L greater than or equal to 0, every point X in CL has the same number CL of neighbors in CL minus 1, and the same number BL of neighbors in CL plus 1. Let me give a simple example. In the n-cube graph, every singleton code, C is equal to X, is a completely regular code. For example, in this picture, you can see the 3-cube graph. The red vertex is your code. The blue versus, yellow versus, and the green vertex are at the instance of 1, 2, and 3, respectively. We can interpret the concept of completely regular code with a matrix. For example, for this example, the entry 2 here shows that every vertex in C1 has exactly 2 adjacent vertices in C2. I mean that every vertex in blue has 2 adjacent vertices in yellow. And this happens for every vertex in blue. For example, this vertex in blue has 2 adjacent vertices in yellow. And it happens for this vertex. There are some interesting points about completely regular code. For example, Neumayer in 1992 proved that C is completely regular code if and only if there is a matrix L such that the cardinal of n of x intersection Cj is equal to Lij, where L is tridiagonal matrix, like this. That Bi and Ci comes from the definition of completely regular code, and Ai is equal to K minus Bi minus Ci. That K is the degree of the graph. Completely regular codes were introduced by Del Sorte in 1973. The next point is that in 1973, Del Sorte conjectured the non-existence of non-trivial perfect codes in Johnson graphs. And in 1992, Neumayer proved that in distance regular graphs, C is completely regular code if and only if it is perfect. Okay, let us give the main definition of this type that is very similar to the definition of completely regular codes. For a graph G and an integer m, a map T from V of G to the set of from 1 to m is called the perfect M coloring with matrix A if it is surjective, and for all I and j, for every vertex of color I, the number of its neighbors of color j is equal to aij. The matrix A is called the parameter matrix, our perfect coloring. There is another term for perfect M coloring in the literature as equitable partition. And you can see that the main difference between perfect M coloring and completely regular code is that the matrix in perfect coloring is not necessarily tridiagonal, but the matrix in completely regular code is tridiagonal. And here is another definition for completely regular code by equitable partition. If C is a subset of V of G is completely regular code, then the distance partition of C is equitable. Here we give some important and interesting remarks and theorems about perfect M colorings. By these theorems, we can show that there are no perfect colorings with a definite matrix. It's a beautiful theorem proof that can be found in Gotzel and Royal in 2001. Let T be a perfect M coloring of G, then every eigenvalue of the parameter matrix is an eigenvalue of the adjacency matrix of G. The next remark is about the sum of every row. Let T be a perfect coloring of a k-regular graph G, then the sum of every row in the parameter matrix is equal to k. It is easy to prove. For example, for a perfect coloring with the matrix A, B, C, D, consider a white vertex. It has k adjacent vertices that A of them is white and B of them is black. So L plus B is equal to k. Next remark says that let T be a perfect coloring of a connected graph G with the parameter matrix A, B, C, D, then B and C is not equal to 0. If B and C is equal to 0, then there are no vertices between, there are no passes between white vertices and black vertices, so the graph is disconnected. The next remark says that if G has a perfect two-column with the matrix A, B, C, D, then it has a perfect two-column with the matrix D, C, B, A. Just substitute the white vertices by black vertices, you can get your desired result. We consider, so after this remark, we consider perfect two colorings up to renaming the colors. So the above matrices are the same up to renaming the colors. When we are going to enumerate parameter matrices for a definite graph, we consider these two graphs just by one. The next proposition counts the white vertices in a perfect two coloring. This is a proposition by Avgasinovich in 2008. If W is the set of white vertices in a perfect two coloring of a graph G with the matrix A, B, C, D, then the kernel of W is the kernel of B of G multiplied by C over B plus C. Okay. Well, we are going to enumerate all the parameter matrices for the octahedral graph. The octahedral graph is a four regular connected graph, hence the parameter matrix of a perfect two coloring must be one of the following matrices. At first, we provide a list of matrices that the sum of whose rows is equal to 4. You can see here matrices that the first row is 0, 4, and the second row is 4, 0, 3, 1, 2, 2, 1, 3, and 0, 4 is not possible because your graph is a connected graph. We provide a list from the remarks we had before. For the matrix 0, 4, 4, 0, the eigenvalues are 4 and 0 minus 4, minus 4. As the distinct eigenvalues of the octahedral graph are the numbers -2, 3, and 4, we conclude that the octahedral graph can have perfect two-coloring only with following matrices. You can see here that eigenvalues of this matrix is 4 and -2. They are the eigenvalues of the octahedral graph. From the proposition of counting the white verses, it follows that there are no perfect colorings with the matrices 1, 3, 1, 3, and 1, 3, 3, 1. So there are only two matrices that can have perfect two colorings. You can see here perfect two colorings with the matrix 2, 2, 2, 2, and here with the matrix 0, 4, 2, 2. So in this talk, we are going to enumerate parameter matrices that there is a perfect two coloring for that matrix. Okay, let us start the main part of our results about perfect two coloring of G, P, N, and K. This is the definition of G, P, N, and K. We have N versus AI and N versus BI. AIs form a cycle, and each AI is adjacent to BI, and each BI is adjacent to BI plus K. It is obvious that G, P, N, and K is a three-regular connected graph. So a parameter matrix by the given remarks we had before, the parameter matrix of a perfect two coloring for G, P, N, and K must be one of the following matrices, these 6 matrices. Now we are going to check that whether there is a perfect two coloring with the given matrices or not. If there is one perfect two coloring, we give the construction, otherwise we prove that there are no perfect two colorings. This is the first one, the first theorem. All of the generalized Petersen graphs, G, P, N, and K, have a perfect two coloring with the matrix A1. So we just give a construction, white, color AI white and color BI black. It gives a perfect two coloring of G, P, N, and K for the matrix with the matrix A1. The second theorem is about perfect two colorings with the matrix A2. The graph GP 3M and K, where 3 doesn't divide K, has a perfect two coloring with the matrix A2 and for each positive integer M. And when 3 doesn't divide N, the graph GP, N, and K have no perfect colorings with the matrix A2. For the first part, we give a construction like this. And for the second one, we can use the proposition for counting the verses, the white verses. It is easy to prove that the second one.
Before you go on, Hamid, we have a question in the chat. I think it's about the structure of the generalized Petersen.
Okay, I cannot see the chat.
So the question asks if the A's form a path and the B's form a complete graph, a subgraph. And I think that's in reference to the definition of the generalized Petersen graph. And we're just looking for clarity on that. But
the definition of generalized Petersen graphs, okay. Sorry. Can you repeat again?
Well, so we're starting to get answers in the chat. Just sort of a question of what the graph looks like. You're saying we've got this outer cycle, and then I think there's some question of what these are doing, and they're giving you some cycle.
Yes, there's a cycle. AI forms a cycle, and BI, every BI is adjacent to BI plus K. For example, GP5 and 2 is a Petersen graph. It has 10 vertices. 5 vertices form a cycle, and 5 internal vertices is adjacent 2 by 2. Okay.
Okay. Great. Looks like it's resolved. Thanks.
Okay. For each perfect 2 coloring, T of GP and K, where K is a positive even integer or 4 doesn't divide n, with the matrix A3, there are 2 vertices that they are the same color. It is a beautiful lemma. This lemma is not valid when K is odd and n is 4m. For example, this construction shows that the given mapping is a perfect 2 coloring with the matrix A3 and different colorings of AI and BI. So in every perfect 2 coloring of GP and K, by this condition, there are 2 vertices, AI and BI, that they have they're the same color. Here is a sketch of the proof of the lemma. Suppose that the assertion of the lemma is false. So there's a perfect coloring with the matrix A3. By removing the X, AI, BI from GP and K, we obtain a perfect 2 coloring with the matrix 1, 1, 1, 1, where A, N, and K is the subgraph of GP and K consisting of the versus AI, and B and K is the subgraph of consisting of the versus BI. So after some computation, we obtain that n is 4m for some positive integer m. That was this, and after that, when K is a positive even integer, we get a contradiction. So the lemma is true. And by the lemma we had, we proved that there are no perfect 2 colorings of GP and 2 with the matrix A3. Contrary to our claim, we suppose that there's a perfect 2 coloring of GP and 2 with the matrix A3. By lemma, there are 2 vertices AI and BI that they are the same color, and after some computation we can get a contradiction. So there are no perfect 2 colorings of GP and 2. For perfect 2 colorings with the matrix A4, we have a similar lemma for this one, like the matrix A3. For each perfect 2 coloring of GP and K with the matrix A4, there are 2 versus AI and BI that they are the same color. The proof is completely similar to the last one. We remove the S, AI and BI from GP and K. We obtain a perfect 2 coloring with the matrix 0, 2, 0, 2. And after some computation, I think, we get a contradiction. By this lemma, we prove that there are no perfect 2 colorings of GPN and 2 with the matrix A4. For the matrix A5, GP5M and 2 graphs have a perfect two-coloring with the matrix A5, GPN and 2 graphs for n such that 5 doesn't divide n have no perfect two-colorings with the matrix A5. For the second part, for the first part, we give a construction, and the second part is trivial by the preposition for counting the vertices, the white vertices in the graph. And this is another theorem that proof is similar to the lemma. The graph GPN and K, where n is even and k is odd, has a perfect two-coloring with the matrix A6, although the graph GPN and K, where n is not even or k is not odd, has no perfect two-coloring with the matrix A6. Suppose that T is a perfect two-coloring with the matrix A6. By removing the S, BI, we obtain a perfect two-coloring with the matrix 0 to 0. We can assume that T of A sub is equal to 1. After some computation, this gives n is even and k is odd. And for the first part, this mapping gives a perfect two-coloring with the matrix A6. Okay, as we said, the problem of existence of perfect two-colorings for GP, N, and K with the matrices A1 and A6 is closed. So we just consider the matrices A2, A3, A4, and A5 for GP, N, and 3. This theorem says that the graphs GP, N, and 3 have no perfect two-colorings with the matrix A2. Here is the sketch of the proof. At first, we proved that for each perfect two-coloring of GPN and 3 with the matrix A2, there are no consecutive versus AI and AI plus 1, such that they are the same color, they are black, actually. Then we suppose that there is a perfect two-coloring and we get a contradiction. For the matrix A3, for GPN and 3, all of the graphs, GPN and 3, where A is even, have a perfect two-coloring with the matrix A3, and there are no perfect two-colorings of GPN and 3, where n is odd with the matrix A3. For the first part, consider the mapping. This mapping shows that this mapping is a construction for a perfect two-coloring of GPN and 3 with the matrix A3 when n is even. And to prove the second part, we suppose that there's a perfect two-coloring of GPN and 3 with the matrix A3. By lemma, we had a lemma for GPN and 2. It is useful for GPN and 3. By lemma with no loss of generality, there were two verses that they are the same color. We suppose that they are white, and we have two following cases after some computation for some positive integer I. We get this, that it gives n is equal to 10m, which contradicts n is odd. And for another case, we get a contradiction by getting this. And this is a theorem for a perfect two-coloring with the matrix A4. All of the graphs GPN and 3 where 4 divide n have a perfect two coloring with the matrix A4, although there are no perfect two coloring of GP and N3, where 4 doesn't divide N with this matrix. For the first part, consider the mapping T. It gives a perfect two coloring with the matrix A4 for GP and N3. And to prove the second part, we suppose that there is a perfect two coloring of GP and N3 with the matrix A4. Again, we have two cases. In both cases, we get a contradiction. Here we generalize the theorem for GP NN2 with the matrix A5. The graphs GP5M and 5T plus 2 and 5M 5T plus 3 have a perfect two coloring with the matrix A5. And these graphs, where 5 doesn't divide N, have no perfect two colorings with the matrix A5. For the first part, it is a construction, and the second part is trivial by the proposition. Here you can see a summary of the results for GP for enumerating parameter matrices for GP and NK. For example, you can see all of the graphs GP and N2 and GP and N3. The parameter matrices are enumerated for the general case GP and NK. For the matrix A1 and A6, the problem is closed. And for the matrices A2 to A5, it is open problem. Okay, let us start. Perfect three colorings of GP and NK. The simplest necessary condition for the existence of a perfect three colorings of a cubic connected graph with the matrix, with this matrix, is that A plus B plus C is equal to B plus E plus F is equal to G plus H plus I is equal to 3. It means that the sum of every row is equal to the degree of the graph, that is 3. Also, it is clear that we cannot have B equal to C equal to 0 and D equal to F equal to 0 or G equal to H equal to 0, because if B and C equal to 0, then there are no passes between white versus and black versus and red versus. So the graph is disconnected. So we cannot have this condition. In addition, B is equal to 0 if and only if B is equal to 0, because if B is equal to 0, it means that there are no passes between white versus and black versus. So there are no passes between black versus and white versus. It follows that D is equal to 0 too. And this one. By using the conditions above and C++ programming, it can be seen that there are only 109 matrices that can be a parameter matrix corresponding to a perfect two coloring in a cubic connected graph. As we had in the perfect two coloring, we consider all perfect three colorings up to renaming the colors. We identify the perfect three colorings with the matrices, these 5 matrices, obtained by switching the colors with the original coloring. So we consider 6 matrices with this one as one when we are going to enumerate parameter matrices for perfect three coloring. By using this condition and some computation, it is clear that we should consider 22 out of 109 matrices. These matrices are listed in the next slide. Actually, a cubic connected graph that only have perfect tree colorings only with these 22 matrices. This is a proposition for counting the white, black, and red verses in a perfect recoloring. Let T be a perfect recoloring with the matrix A. Then we can count the white verses, black verses, and red verses. We have 4 cases. The first case is that B and C and F is not equal to 0. The next one is that B is equal to 0. We can count the white and black and red verses. If C is equal to 0 and if F is equal to 0. For example, you can see here that if B is equal to 0, this one cannot be defined, and we put FG over CH instead of D over B. If A be a parameter matrix of a k-regular graph, then the eigenvalues of A are lambda 1 and 2, terms of A minus K over 2, plus and minus, radical terms of A minus K over 2, minus det of A over K. You can see the proof by using the condition A plus B plus C. All of this is equal to K. It is clear that one of the eigenvalues is K. Therefore, det of A is K lambda 1 lambda 2. From lambda 2 is trace of A minus lambda 1 minus K. We get det of A is equal to minus K lambda 1 plus K trace of A minus K lambda 1. And by solving the equation, we obtain the desired results. And by using the theorems, the remarks we gave in a perfect recoloring for a cubic connected graph, we can easily prove these theorems. The Petersen graph has perfect recolorings with the matrices, with the matrix this one and this one. And the graph GP 6 and 2 has perfect recolorings only with these matrices. And the graph GP 7 and 2 has no perfect recolorings. Okay, thank you for your attention.
Well, thank you for the talk. Let's thank Hama.
Thank you very much.
Thank you.
So, do we have questions for Hamid?
Could he show us the matrices A1 through A6 again for the 2 colorings?
Yeah, did you get that? We'd like to see the matrices.
6 matrices. Okay.
Thank you.
I'll ask a sort of random tangential question, but I'm this talk made me wonder if there's some sort of graph polynomial like the chromatic polynomial that you can cook up for perfect colorings. Just sort of like, if there's some polynomial you can come up with that counts them in any sort of nice way.
You mean that it is related to binomial? Chromatic?
Yeah, I mean, so if you just have graph colorings, not perfect colorings, then You could come
vertex
up with a
color.
polynomial that counts the number of colorings, the different numbers of colors. That's a polynomial.
I think this coloring is a partition.
Right.
It makes a partition for the graph, and it is not related to adjacency, adjacent versus. Okay.
So you'd have to come up with some sort of generating function for partition to properly not save anything. Fair enough.
May I ask another question?
Yes, of course.
Is it clear which of these colorings arise as orbit partitions of some subgroup of the automorphism group? So the automorphism group is, well, it probably contains more than the dihedral group, right? There could be something that swaps the inner and outer cycle, as there is in the Petersen graph.
Yes, we have an orbit partition when it comes from orbit coloring, and every orbit coloring is a perfect coloring for a graph, and I think that every perfect coloring comes from a block in permutation group. We can define a block. I think every perfect coloring comes from a block.
I didn't catch that word. Comes from a block?
Yes, I can. What?
Can you repeat that, Bill?
He said every perfect coloring comes from a X, and I didn't know the word. I didn't hear the word. Block is the word?
Yes, I can remember when I was a PhD student, we had a course in permutation groups, and I guess that every perfect coloring comes from a block. I cannot remember the definition of blocks.
It's a block of imperativity.
Okay. So every equitable partition comes from a system of imprimativity. Is that the claim?
Sorry.
Okay, I think I understand. Thank you.